Good morning.
Good morning, Dr. Hunter. How are you doing?
Very well. Very well. Got a couple things to
Um,
try to accomplish today, and I'm confident I'm going to make it.
that's good. That's good. Um, I have a question for you today.
What's that?
Um, could you help explain to me heating curves and changes in states of matter? Because I think I understand when you heat something up, it goes from solid to liquid to gas. But I think the graphs and some of the numbers are a little confusing for me.
They are. They are. In fact, I was looking at this, and I found I had to stop and give myself a few minutes to figure out what was going on with those. And I've been doing it for a long time. So yeah, they're not trivial. Let me share my screen. In 5.3c, they talk about changes of state and heating curves and energy. And so I'm just going to go in there and I'm going to try to make sense of what they've got. I think, like almost everybody on the planet, we know that when you heat up something, it gets warmer, right? I mean, what's the point? If you're not get warmer, then you should stop heating. You need a new method. And they've got these two nice graphs in here, but there's a lot going on in them. I mean, there's A to B and B to C and C to D and D to E and E to F, and they both have D's to E's, and it's not clear what's going on in there. And so let's open up that figure like they suggest and take a look at it. So they have a graph, and as we've talked about before, when you approach the graph, let's look at the axes first, right? And so here it says quantity of energy transferred, right? So this is the amount of energy across the bottom on the horizontal axis, and it's got the temperature on the vertical axis. And so I apparently can take one gram of water or 1 gram of benzene by selecting those, and I can add heat to it. So let's start with water and see what happens. And a blue line appears. And I think what that means is, okay, before I get started, I'm starting off here. I've not put any heat in. So I'm down here near the 0 mark. So I add the heat. Oh, look, I add the energy, right? And what happens? Oh, it starts to go up along this line here. And that says the temperature of the water is increasing from, what was it before? It was -50. So it's solid, right? It's solid ice at -50, and I add energy to it, and the temperature starts to go up until I get to this point. 0 degrees Celsius. That's the melting point of solid ice. So here's a graph, a line that shows adding energy to ice will change it from -50 to 0 degrees pretty uniformly. And apparently it takes 100 joules to do that. Great. So at this point, what's going on? We're still adding energy, right? Because I'm still going across this horizontal line, but the temperature is not increasing anymore. And if you're at all familiar with these graphs, you know that is the point at which the melting takes place. So we're adding energy, but the temperature is not changing. All that's happening is the molecules are going from being in this solid structure to the next stage, which we know is liquid. And so across this horizontal part of this graph, the water is gaining energy as we add heat to it, but the temperature is not increasing. At this point, all the water has melted. So it's now liquid water. And as we continue to add energy to it, as we continue to move to the right, the temperature begins to increase some more. Okay so far?
Okay, so
Yeah, go ahead.
So then you could say when it's increasing in temperature, that's the one state of matter that's warming up, right? That's
right.
That's
yes.
On the left, it's the ice, the solid water, and then on the right, where it's increasing again, that would be liquid water.
Correct. Correct. Yeah. Nice. Yeah. Good job pointing that out. Yeah. So I think that's, um, but there's a lot going on, right? I mean, we've got a couple of different things, and it gets to it as you click on through this activity. The questions that are asked you get more and more pointed about this particular graph. Let's look at benzene. If we know that for water, let's look at benzene. So let's reset the thing, and let's do it for benzene. Red line. What does this tell us? Well, it looks a little bit the same shape. It's got this part where as we're adding energy to it, as we're going across horizontally, it's also going up vertically. So this is probably solid benzene warming up to its to the next stage. I wonder if that's actually solid benzene or liquid benzene.
Yeah, I was thinking that as well.
I don't think it tells us here, but I'm guessing it is, because I don't think benzene would freeze at this temperature. Oh, this would tell us this would be the freezing temperature, but I suspect it's actually the boiling temperature of benzene at what looks like around 10 degrees or so, 10 degrees Celsius. I think we should look up the boiling and melting temperatures of benzene.
Oh, so then you could say the straight line then could be like a boiling or melting point.
Correct. Yeah. I mean, clearly going as we're adding energy here, the temperature isn't increasing. So this is clearly a change of state again for benzene, going from one state of matter over to this other state of matter. And so we're putting in energy, but the temperature doesn't increase because it's a single change of state.
Okay.
And then over here, the temperature begins to increase again as we add the energy. And that tells us that this new state of matter, which I think is probably a gas, is increasing in temperature as we add more energy to it.
Okay.
How does that work for you?
That makes sense.
Okay. So let's look at some of the questions that it shows here. So, all right. So generate the heating graph for water. Okay, I can do that. So let's reset the whole thing. Click on water and click on add heat. All right. So I've generated the heating graph for water. How much energy is required to heat solid water from -50 to the melting point of 0 degrees Celsius? So I want to go from -50 to 0 degrees Celsius, and I want to know how much energy is required. So if I come across here to this point, to that point, it looks like it's 100 joules. That's what I get for that. Is that what you get looking at that, Kevin?
Yeah.
Okay, so let's type in 100, see what happens. So I submit that. Oh, got it correct. Woohoo! Very exciting. Yeah, and it tells me that I got the correction correct and why I got it correct. So that's nice. All right, next question. All right. Which requires more energy? Heating 1 gram of solid water from -50 to its melting point, or melting the solid at 0 degrees Celsius? Okay, hold on now. So which requires more energy? Heating 1 gram of solid water from 50 to its melting point. So going from -50 to its melting point, how much energy does that require? That's 100 joules. Or melting the solid at 0 degrees. So doing this melting process goes from 150 over to, looks like about 425, 430, something like that. So this is 330 joules to do the melting the solid, 100 joules to heat the solid. So I'm going to say, which requires more energy? I'm going to say the melting requires more energy. You agree with that answer, Kevin?
Yeah, and it's a little tricky too, right? Because we know that when it's melting, the temperature isn't increasing, which for most of us is a telltale sign that there's some sort of energy. But it takes a lot to break those forces that keep the solid together and to break them to get them to the liquid phase, right?
Right, right. And looking at the graph, if I look at this graph, I say, ooh, look at this. It goes up a lot here. Doesn't go up at all. This must be more energy. But it's not. That's just the temperature, right? In fact, actually, if you turn your head sideways, or actually I got to turn it the other way so it matches, this distance here is small, and this distance is large, right? And
Yeah.
so this one is more energy. So you and I are pretty convinced on the melting. So let's click on submit there, and hooray, we got it correct. Over 3 times as much. What did we say? We said 330 compared to 100. Yeah, so we were all over this one. We nailed that one, Kevin. All right, let's try the next question. All right, which has the greater specific heat capacity, solid water or liquid water? When I saw this question earlier today, I thought, I have no idea what I'm doing. But then I figured it out, so that was good. Because it's what they're really asking is, does it take more energy to heat up solid water than it does to heat liquid water up by a particular degree? And so what I saw was that going from minus 50 to 0 required 100 joules. But going from 0 to 50 either requires more energy or less energy. So look at this. Here's 100, 200, 200 and 220 joules or so, something like that, to get the liquid water up to 50 degrees. So the substance that requires more energy to change by 50 degrees is not this solid. This liquid is the one that requires more energy. And so it has the greater specific heat capacity. Go ahead.
So specific heat capacity is just the amount of energy some sort of substance requires to heat it up. Is that what it is?
Effectively, yes. I mean, I think it's defined as the amount of energy required to change 1 gram of a substance by 1 degree Celsius. But it basically says the more that a substance can absorb absorb heat, the greater its heat capacity is. And here we see that water can absorb it so well that it takes 220 or 230 joules of energy to get it to go up by 50 degrees. Solid water doesn't have quite such a good heat capacity, and so it only takes 100 joules to make it go up by that same number of degrees. So I want to say the answer is liquid water. And again, the graph is tricky because you say, which one has greater? Well, it's kind of shown by the slopes. But ironically, the steeper slope is not the right answer here. The shallower slope is the right answer because it goes up more slowly, right? And so it takes more energy to get it to change by 50 degrees. So I'm on liquid here. Oh yeah, we're 3 for 6 so far. Oh yeah, look at this. Notice that the slope for the heating the liquid is more shallow than for heating the solid. This means more energy is required to heat the liquid per degree than is required to heat the solid. Nice.
Exactly what you said. All right.
Say that again?
Exactly what you said.
I know. We rock at this apparently, Kevin. All right. Now compare the heating graph for water with that for benzene. All right. So, okay, there's the benzene graph. Which has the higher melting point? I think I know this one because this was the melting temperature for water, right?
Mm-hmm.
Horizontal means that it's changing from liquid to solid. From solid to liquid. And so from solid to liquid. Oh, and apparently this is about melting point. So apparently this is the melting temperature for benzene. And I would say which one has which has the higher melting point? I say water melts at 0 degrees Celsius. I think benzene apparently melts at about 10 degrees Celsius. And so I want to say benzene for this one. What do you think?
I'd agree.
Oh, 5.5. What did I say? 12?
10?
Hmm, hmm. I think I like my reading of the graph better than I like their reading of the graph.
Or maybe they need to graph it better.
I don't know. Okay, let's. I'm guessing that they actually looked up the melting point for benzene, whereas you and I didn't. So I'm going to assume their 5.5 is right. I don't like their graphing skills.
Agreed.
Okay. I will spot them that it is a higher temperature than 0 degrees, and so therefore the answer to the question is correct. Okay, moving on. All right. Okay, which has the greater heat of fusion, ice or benzene? Okay, now we got to think about this one. Heat of fusion. This means which one requires more energy to change from solid to liquid, right? It's heat of fusion, so that's the opposite of melting, right? But it's the same place on the graph. Ice or benzene, which has the greater heat of fusion? Okay, so we know water takes, what did we say, from 100 and to 430. So it takes about 330 joules to convert 1 gram of water. That's what we figured out from that graph. From the red graph, we see it's, well, who knows how we're reading this thing anyway now. It looks like 75 to me. 75 to 200 is about 125. So this is about 125 joules to change the gram of benzene, 330 joules to change the gram of ice. And so I think ice has a greater heat of fusion.
Yeah,
What
that
do you
makes
think?
sense.
Does that work for
It's,
you like that, Kevin?
yeah, it's just like the longer horizontal line.
Yeah, yeah, I think so, yeah. So what happens, ice. Quick. Notice that the quantity of heat added to convert ice is over 300 joules, and benzene is less than half that. Okay, I agree with their math this time. Okay, nice. Okay, next question. One more to go. Which has the greater specific heat capacity, liquid water or liquid benzene? Okay, now, this is an interesting one, right? I mean, there's a lot going on here. So the greater specific heat capacity, liquid water. All right, liquid water. Liquid water is this part of the blue curve, right? Because it's gone from, this is where it finishes melting and it starts to warm up some more, right? The temperature starts to go up. So we got liquid water versus liquid benzene. Okay, which one has the greater? So to get water from 0 to 50, we decided it was 230 or so, right?
Mm-hmm.
To get benzene from apparently 5.5 to 50, it's about 75 or so. So I think, again, we keep on adding the energy, but it takes more energy to raise the temperature of the liquid water than it does the liquid benzene, right? Because, again, this slope is more shallow, right? So it takes more energy to get it to go up by any particular, by 1 degree, by 2 degrees, by 5 degrees, by 10 degrees, right? It takes less energy to get the benzene to go up. Yeah, that's a tough question. There's a lot going on. It's just two simple little graphs. How could a question like that be so hard? Well, it's hard because there's a lot going on. So I think the answer is liquid water. Bingo, 6 for 6, look at that. Notice that the heating graph for benzene increases very steeply compared to that for liquid water. Yeah, steep, right? Goes up more quickly, less heat capacity. Goes up more slowly, more heat capacity. This means less energy is required to heat the given mass of benzene by a set temperature change than needed for the same mass of water. Module complete. Oh yeah, I rock at this. Okay, what do you think of those, Kevin?
Yeah, I think those questions were pretty helpful. I think there's just some terminology that's a little hard to understand at first, like specific heat capacity, heat of fusion. But I think if you work through it, maybe this helped a little bit. Use the graph. I think you can get it down.
Yeah. And don't be shy about going through it slowly. There's just a lot going on in these graphs, right? It seems like just two little simple lines. How hard can it be? Yeah, well, there's a lot going on. I had to look at it a couple of times before I could figure out what was going on. If you can read that kind of graph, I mean, it's a place where there's a real scientific set of skills in there that people can use no matter what they go into. There's a real set of life skills in there that you're confronted with graphical information. You have to try to figure out what it might mean. But it's there. You can do that. If you can handle those heating cooling curves, you can handle an awful lot.
Yeah, it's pretty tough stuff. All right then.
Okay.
I think that's all then.
Yeah, really nice to talk to you, Kevin. Thank you.
Yep. Thank you, Dr. Hunter.